Hi, everybody. We're live again with another cool jobs interview. And today I have Liz Matson. She is an instrument systems engineer at NASA. So Liz, why don't you tell us a little bit about what you do?
Sure. So I'm an instrument systems engineer. At Goddard, we build spacecraft like the one you see behind me, OSIRIS-REx, that goes to, I've worked on things that are currently orbiting the moon. I've worked on things that are orbiting Earth. This one, OSIRIS-REx, is orbiting an asteroid named Bennu. And right now, I'm working on something that is going to the Trojan asteroids that share an orbit with Jupiter, which is pretty cool. And my job as a systems engineer is to make sure that all the different parts come together like a big, complicated puzzle, that everything fits how it's supposed to fit. So we have a thermal group that works on their stuff to make sure that all the temperatures are what they need to be, and we have optics, and we have mechanical and electrical, and I help bring all those pieces together to make sure it works how it's supposed to work.
Okay, very cool. So what kind of things did you have to study in school to become an engineer?
So I majored in mechanical engineering. So in high school, I did a lot of math and calculus, and I took AP physics. And then I went to college and took even more math and more science, and I got my bachelor's in mechanical engineering, and then I went back for my master's. After working for a couple of years, I went to Maryland to get my master's in aerospace.
Aerospace engineering, very cool. Were you working at NASA when you did that?
I did, and they paid for it, so thank you, taxpayers.
Very nice, very nice. So that's a good way to get your advanced degree, is get a job somewhere that they'll pay for it.
Exactly, and the benefit of that, because I worked for 3 years, and then I went back to get my master's, so it was a really good opportunity to figure out what I wanted to do before investing the time to get that degree, so that was helpful.
Okay. Now, if any kids are watching, we've got a few people watching, just go ahead and if you have a question, have your parent comment them, and we'll ask her. You can see I can put comments on the screen. That was just a comment that I put in the comments earlier. So if you do have a question, please ask them, and we'll make sure that they get to Liz. And in the meantime, I have lots of questions. I always have questions for these. So I'll keep asking my questions until we get any questions from the kids. And actually, let me ask Parker. Parker, do you have any questions? Parker's my son sitting here. You have any questions?
No.
He's looking at me like a deer in the headlights. He doesn't have any questions yet, but he might have some. He looked interested.
About Jupiter.
Oh, Jupiter, yeah. So we were talking about Jupiter, and he wants to know a little bit. What can you tell us a little bit about the asteroids that are that have an orbit near Jupiter?
Very little. So as an engineer, it's my job to make sure that the scientists get the data that they need. Unfortunately, I don't always, not that I don't pay attention, because I'm big fan of all of our scientists at Goddard. And Goddard actually has the biggest group of scientists anywhere in the world. I mean, there are 10,000 employees at Goddard. I don't remember how many of them are scientists. We have more scientists at Goddard than anywhere else, all different kinds of scientists. I work with a lot of planetary scientists who are, have been really great to work with. The instrument that I'm working on, actually this one and the one that's orbiting Bennu, behind me, OSIRIS-REx, they have been infrared spectrometers. So that means, oh, and I just see a question from Sonia about what kind of data my machines collect. So that's a great segue. So they're both infrared instruments. So they're measuring infrared data to try to figure out what the asteroids are made out of. So they can read that data through an infrared detector and try to figure out the chemical composition.
Okay. And what about some of the other instruments that you create, that you've worked on? Do they collect similar types of data, different types of data?
So one of my favorites is the Lunar Orbiter Laser Altimeter, LOLA, which is on the Lunar Reconnaissance Orbiter right now, orbiting the moon. And I know that it is 10.5 years old, because it's just a month older than my son. It launched right before he was born. So I'll always know Elro's birthday. A laser altimeter is a fancy word for saying it's a laser that, let's see, where's my camera? Okay, so we have a laser shooting at the surface of the moon, and it will calculate how long it takes for that light to bounce back and hit the receiver telescope tube. And rate times time equals distance, and the speed of light is always the same. So the laser, oh, hi Amy. So the laser will measure the surface of the moon. So there have been a lot of really fancy maps coming out of LRO in the last 10 years, topographical maps, which basically say, okay, these are the high points. They usually come out as red on the map, and then there are the blue and the purple ones that show the craters on the moon. So LRO collected a lot of that data, and that was really awesome. Okay. There's another infrared satellite I worked on that is actually orbiting the Earth on Landsat 8. And that's really neat because it collects temperature data of Earth, which obviously is really important for, and this is Earth Day this week, so studying temperature data. But what's cool about Landsat 8 is that it can measure groundwater. So Western farmers use that data to know how much they need to water their crops, what their irrigation system needs to look like. And scientists from all over the world have been able to use that data looking at groundwater measurements to actually track malaria breakouts before they happen. Because if you know where the land water is, you know where mosquitoes are going to be, and you can try to combat malaria before a big breakout. So we do a lot of really cool stuff with a lot of different implications for science.
Very cool. Amy said hi, so I'll just put that up on the screen. And then Will has a question from Kelly. How do thrusters come back to Earth?
So when we launch our satellites, they're on a really big rocket. And the rockets usually have to have a couple different stages, what you talked about with the thrusters. The thrusters don't actually make it all the way out into Earth orbit, so they just kind of fall down with gravity. And the reason we launch from Florida and the couple other different places we launch from are so those thrusters fall back into the ocean and don't hit anybody. That's really very important. NASA spends a lot of time looking at how what our rockets are going to do and how they fall back to Earth, and even our satellites who have been in orbit. Hubble's been up there for, I think it's almost its 30th birthday.
Wow. For
Hubble. It won't last forever, so eventually it's going to have to come back to Earth with a controlled entry so that it also lands in the ocean. There are a lot of rules on how we need to make sure we keep people safe for that.
Mm-hmm. Now, the instruments that you send into space, do they all come back, or do some of them stay up there? Or stay out there?
The one orbiting the moon is eventually probably going to hit the surface of the moon eventually. It takes a long time, so it might just orbit the moon for a really long time. OSIRIS-REx is actually going to send a capsule back to Earth, I think about 3 years from now. It's a sample return mission. So they actually just did a rehearsal orbiting the asteroid and trying to get as close as it can. They have an arm, I don't know where my camera is. So they have a robotic arm that takes a little poof of air and then collects that. It's actually called regolith, asteroid dust. And we'll bring that sample back to Earth. It's going to hit somewhere in the desert 3 years from now, but most of the rest of the satellite will stay up there.
Okay. All right. Now, why do you have machines do all this instead of people? Why do machines go out and measure all these things instead of people?
Well, it's safer for the machines. Obviously, so my instrument is about the size of a shoebox. And it doesn't need food, it doesn't need water, it doesn't need air So launching that machine, or little telescope really, is a lot safer and less expensive than sending people
Okay.
to do it.
Makes sense. Makes absolute sense, right, kids? We always talk about that when we talk about robots, that robots can do a lot of jobs that people shouldn't or can't.
Right. Mm-hmm.
Yeah. We have a question from John. He wants to know if you work with JHUAPL at all on missions, or do Goddard and APL fly their own spacecraft and have different missions?
So it depends on the mission. I know some people at APL. I think Messenger or New Horizons were Goddard, and Goddard had an instrument that was APL managed. It kind of depends on how the how headquarters decides who runs what. There is some overlap. We do some similar things, and we work together on some things. I have not. So we fly our. Oh well, sometimes we work together. Most of the time,
Okay.
not.
Okay.
I was there for a vibration test once because they had in my old job as a mechanical engineer, I was in charge of vibration testing. So if you picture a rocket, it's not a very smooth ride. It shakes a whole lot on the way up. And we need to make sure that our instrument is going to survive that. So we do ground testing on big shaker tables here, and we shake it before it goes up. And a couple of years ago, our shaker tables were really busy. So we asked APL if we could borrow theirs, and I went up there for a test, and they were very nice.
Okay. And for any kids that don't know, what does APL stand for?
Applied Physics Lab.
Okay.
I'm gonna go Applied Physics
John,
Lab.
if you're still watching, John, and you know, make so to confirm or tell us what it means, because I'm not sure. I don't even know. I know JHU is Johns Hopkins University.
Sounds right. Yep, a lot of acronyms at NASA and government-wide, a lot of acronyms. So if I talk in acronyms, I apologize for that.
Okay. And John says yes, that's what it stands for.
Okay,
so,
excellent.
What does NASA stand for?
National Aeronautics and Space Administration. Okay. So there are 10 different centers at NASA. When you think about NASA, you mostly think of astronauts, right? So you have the astronauts who train in Houston, and then you have the launches that happen in Florida, but we have a lot of different centers. So the aeronautics part is really looking at more airplanes and aerodynamics. They do a lot of that out in California at Dryden, which maybe isn't called Dryden anymore, and Ames. So I think it's John Glenn. Nope. That's Cleveland. So the Cleveland one also has a really big wind tunnel. And we do a lot of aeronautics in addition to the space stuff you think about. Goddard and JPL, Jet Propulsion Lab, out in California are the two that do the most of this planetary robotics stuff that I do.
Okay. Have you ever been to space?
I have not. I get asked that every time I go to my kids' career days, and people are pretty disappointed. I've seen 2 launches. That's as a VIP. That's the closest I've gotten. I get motion sick, so I think I'm good just, staying on the ground.
So that was my other question is, would you want to go to space if you could?
I did actually apply. I applied for the astronaut corps maybe 15 years ago, and I made it through like 2 levels with 10,000 other qualified applicants. I didn't get that far, and that's okay with me. I wouldn't pass the physical, so that's.
Have you ever been on the ride at Disney at Epcot, the space ride, where it's like a simulated space trip?
I have, right after eating poutine in Canada, and I would not recommend that.
Yes. Yeah, I agree. All right, we have a question. I'm not sure how are rockets did rent? I'm not sure what you're asking there. How are rockets different? Maybe?
Or sent, or
how are rockets sent? Let's say how are rockets sent? How are rockets sent into space?
So you have to have a lot of force to overcome Earth's gravity So we have rocket boosters. Someone else asked about that, with a couple different stages, different kinds of rockets, depending on how heavy it is, what you're trying to lift, and how far you're trying to go. So some rocket engines are, like if you think of the space shuttle, which maybe kids won't remember, the space shuttle has been retired for a while, but you had that big orange tank and then the two side tanks. So that mixed hydrogen and oxygen together to make a big chemical reaction that created a lot of force to push it up. And you've got the solid rocket boosters, which are also a chemical reaction, but a little bit different. They had a solid in there, think closer to like a candle burning. But yeah, things burn and explode, and then the engines make that force point in a certain way, so the rocket can only go up, we hope.
Okay. Oh, okay. To clarify the question, how are rockets different than missiles?
Well, the physics of them are the same. I think it's where they're pointed, and probably how much thrust they have going up. But yeah, the shapes look pretty similar. The science is similar. Actually, our space rockets in the 50s and 60s were developed by World War II missile scientists. So it's a lot of the same science and physics there.
Okay, very cool. So just a reminder, if you have any questions, please go ahead and comment them, and we'll ask Liz what your questions are, and she will answer them live. We've got some time left, so I'm going to keep asking some questions. So let's see. Next question that I actually have a few questions from some Girl Scouts. There are several Girl Scouts watching this series, and every time we interview a woman, they ask me to ask these questions because they're working on their Amuse journey. And they have to interview women for that. So the first question they have is, are you in a male-dominated field?
For sure. Yes, very much so. Engineering in general is pretty male-dominated. Mechanical and aerospace in particular, especially. Goddard is a really wonderful place to work. It's very diverse. And I was actually talking last week with some other women I graduated with. I think I've had more female supervisors and bosses and mentors than most of my friends, and we've all been in industry for about 15, almost 20 years. So I've been very lucky to be where I am at Goddard and have some really wonderful female role models. At the same time, I'm usually the only woman in meetings, and I'm pretty soft-spoken, so sometimes it's harder for me to have my ideas heard. So what I notice is when I'm in a group of all women, not at work, I'm talking over people and interrupting people, because at work, that's the only way that I can get a word in edgewise. So it's hard for me to then go home and have good manners.
Mm-hmm.
Yes.
Have you ever faced any stereotypes about your job?
No, not that I can think of. I work with a lot of really talented people, men and women of all different backgrounds. Not that I can think of.
Okay. Have there been any women that sort of paved the way for you and that were inspirations for you?
Oh, definitely. There are several female managers who have been mentors and have kind of helped me move from where I was in mechanical now to systems engineering and thinking about maybe project management or leadership down the road, because I think I have like 25 more years before I can retire. My kids are expensive. So I don't know what I want to be when I grow up yet. I'm still kind of figuring it out. And I have time. And one of the great things about Goddard is I can try a lot of different things. It's a big place with a lot of different jobs.
Okay.
But I've had many wonderful female mentors. And male.
How long have you been working at Goddard?
Since 2003. So
okay.
17 years now.
Wow. And you still have like another 20 to go?
I think so.
Okay. We have another question. Do you and NASA construction workers create rockets?
So most of what I do, and actually, since we do have time, after I answer this question, I want to talk a little bit about the engineering design cycle. But most of my job and most of what Goddard does focuses on what sits on top of the rockets and not the rockets themselves. I think our rockets are built down in Michoud. I forget what state that is in. But again, we have 10 NASA centers. Goddard does the sciencey part more than the rockets. So I want to talk a little bit about the engineering life cycle, and probably if you have ever done a science project or have tried to build something even out of cardboard at your house, there are 4 different phases. So there's the design process. So you have an idea and you sketch it out on paper, and then you build it. So design, build, and then after that you're going to want to test it. And when you test something, almost always you learn something you weren't expecting. I know we do. We spend a lot of time planning and building, and still we want to make sure we test it so we understand it, and we're generally pretty surprised. Well, usually we'll learn something new. So then we'll go back and improve. So design, build, test, and improve is the engineering cycle we use at Goddard. We have some fancier words for that, but it's probably also what you might use at home for a science project, or building a big thing of Legos, or I don't know, a cardboard roller coaster in your house. So my job looks a little bit different during the design phase than it does during the test phase. But yeah, in the design phase, we do a lot of drawing on whiteboards. Just kind of it's basically the grown-up equivalent of writing designs on the back of a napkin or something. We're in meetings, we're on whiteboards, and then we analyze it. So in my old job as a mechanical engineer, a lot of my job was trying to figure out if something was going to break before we had to test it, and then actually see if it would survive. So a lot of design and analysis at the beginning. I've been less involved in the actual building part. You asked about construction. I don't do that as much. Testing, I was involved in vibration testing before in my old job. Right now, I'm involved in something called comprehensive performance testing, which is it takes the instrument through all the different things it needs to do. For me, it looks like pressing buttons on a computer to make it do what it's going to do. And it can take many, many hours to do that test. And I've been planning for this test for over a year. So we do a lot of planning before we actually do something.
Now, how do you test things without sending them up into space?
So we do a lot of testing on the ground. So yeah, we don't have a big rocket simulator exactly, but we know what those vibration levels are going to be, so we can simulate that on the ground with the big shaker tables. Sometimes we call our testing shake and bake. So the bake part of it is making sure that our instrument or the whole spacecraft is going to see all the temperatures that it's going to see on orbit. So we do that in our big thermal vacuum chambers. So the bake part of the shake and bake is the thermal vacuum chamber. So we put our instrument in a big chamber, pump it down to vacuum, so no air in it, no atmosphere, because there isn't any atmosphere out in space. And then either heat it up or cool it down and cycle it a few times to make sure it is ready for that and behaves how we think it's going to.
Okay. And what are some of the temperatures? And you just answered John's question. Can you explain what the bake part is of the shake and bake? You do the shake, so what is the bake? What are some of the temperatures that the instruments will be experiencing when they're in space? Are they really, really hot, really, really cold, or both?
A little bit of both. So what I'm working on right now, the coldest it gets is, at least the electronics box part that I'm working on, gets to -50 C. I don't have a calculator on hand to know what that is in Fahrenheit. And 20 degrees Fahrenheit. That's kind of like a warm room, right? Pretty hot room, but it's not like, you know, in the oven kind of hot.
Okay. So a little bit of both. And I guess does it depend on where the instrument is going?
Yes, absolutely. It depends on where. Also, there are different parts. That's one part of our instrument. We have another part that gets down to like 140 degrees Kelvin, which is not quite cryogenic. It matters what kind of detector it is and what temperature that detector needs to be able to work. But also, yes, very much where it's going. So there's some things orbiting the Earth, but closer to the sun than some of the other stuff I work on. I can't think of the name, but they had to make sure that they could survive those hotter temperatures for the ones that are looking at the sun for those measurements.
Mm-hmm. And does NASA, does Goddard work on anything that has been to Mars?
Yeah. Mars SAM, I forget what SAM stands for, something about a sample, why can't I think of it? It's a mass spectrometer, maybe. So it kind of does some of the sniffing to see what some of the materials on Mars might be. I think we're working on something for Mars 2020, but I don't remember what. Goddard usually has kind of a small part in the Mars stuff. A lot of that is done at JPL out in California. Okay.
Now, who comes up with the names for all of these things? Because there's lots of acronyms and lots of really cool names. Who comes up with those?
I'm not really sure. I do have an interesting story. So before, New Horizons, which went out to Pluto, had a telescope named Alice, and Alice was an acronym for something, I don't remember. But then it had a complementary instrument that was measuring different things, but they worked together. So someone decided to call that Ralph, because Alice and Ralph, and it was not going to the moon, but out there. So the Cramdens from, I'm sure none of the kids will get that reference, and maybe not even any of the parents, the Honeymooners. So it was named Ralph, not because it stands for anything, but because it partnered with Alice. I think it's the scientists and their interesting sense of humor.
Okay. And are some of the names related to where it's going or what it's doing? Or a lot of the names are probably related to where it's going?
Yeah. So LRO, the Lunar Reconnaissance Orbiter, that's named that because it's orbiting the moon. Landsat is named that because it's a satellite that does land measurements. What am I working on now? Right now I'm working, so the mission is called Lucy, and that's actually named after the skeleton Lucy, which was the first, not fossil, but so the fossil Lucy gives clues to kind of where humans came from. Similarly, these asteroids in the Trojan belt are going to give clues to how the planets were formed. So I think that's why Lucy was named. That's why my mission is named Lucy, because we're going to learn about our origin, hopefully.
Very cool. Now, what about Osiris Rex? That's a really cool name.
No idea.
No idea. All right. Oh boy. Let's see if let me just check and see if there's any other questions. I don't see any right now. So if you have any last minute questions, please go ahead and ask them. I will send Liz the link. So if she has some time later, if you have any questions after we do the live broadcast, so she can answer them if she has some time. Liz, I want to thank you. This was a really interesting interview. It sounds like you have a really cool, fun job.
Yeah, I do. I like a lot. I hope to go back.
Yeah, and actually, that was one more question. Are you able to do your work while you're are the people from Goddard, are they going into the office, or are you all working from home?
Goddard is closed. We're at stage 4, which means no one is working on hardware unless they're supporting Hubble or anything up in the air now to keep things safe. Most of what I can do is 100% telework. I've actually been working with teams in Kansas and San Antonio for the better part of a year. So we'd already been set up to do, distance conversations. So if I've been able to work with folks in San Antonio, I can work with folks who live in Columbia and Virginia just as easily. I've been really busy looking at test data for some testing that had happened over the last couple of months. Eventually I'm going to run out of test data to look at because the tests have stopped. But for now I'm 100% telework, and yeah, no one is at Goddard right now.
Okay. And we did actually get one more question before you go. Rovers get stuck in sand, so why don't you use robot snakes?
Robot snakes, that's a really good idea. I'm not sure.
I think you have a future engineer here.
I think so. I liked it, John. Good idea.
Yeah. So why don't you use robots? I guess you don't work on those, on the rovers, so you wouldn't know the answer to that one.
No, I've never worked on anything that actually, has landed. A lot of things that orbit, but yeah, nothing that's ever landed. So yeah, it's a good idea.
Awesome. Yeah. All right. Well, thanks again, Liz. I appreciate you taking the time to do this. Do you have any final words before we finish up?
No, thanks. This was really fun.
All right. Well, thank you very much. And everybody, again, if you have any questions, put them in the comments and I will make sure that Liz gets a link to the video. So thanks again, everybody. We'll see you next time.
Thanks.